All right, last video of chapter 4. Oh yeah, let's kick some butt here. So I've got a very difficult relative velocity problem here. Let me click my buttons. I'll let you look at the screen. That button. Okay, this is problem 4.31 and a half. You got a train going to the right 20 meters per second relative to the earth. That's pretty easy. This is going to be I hat, and that's velocity of the train relative to the earth. That's done. Notice you can use lowercase, uppercase, any case goes tonight. All right. So the person throws the ball with some speed, 40 meters per second relative to the train. Well, that tells me that this is a speed, that's the speed of the ball relative to the train. Got it. All right. And notice that's not a vector because we don't know the angle yet. Let's keep reading. And then I know this is a little bit light, I apologize, but here it says, at what angle should the player aim to cause the ball to leave the person's hand, angle it. What is all this junk? Just so we can see this better, the idea is I'm going to throw it at some angle, but it's actually going to fly off at a different angle, right? Because these two velocities are going to affect it. I guess that this train should be driving on the ground, right? So the idea is, which way should I throw it so that it looks like I threw it at 30 degrees, essentially? Now, keep in mind here, what's going to happen to this velocity is whatever velocity vector I throw it at, I'm basically adding 20 to the I hat. When you add 20 to the I hat, that should make the X component of this velocity bigger. So if I want to throw it so that it looks like it goes at 30 degrees, I better throw it up high, which then the X component will get lengthened by 20. And so it's probably going to be something like 50 or 60 meters per second, kind of up at a 50 or 60 degree angle or something, right? And then it'll go off in this direction. So, and maybe you don't have any intuition for those numbers. We don't need any. But what is this piece of information that I gave you? This is not the angle. This is not 30 degrees. I want to aim somewhere so that it looks like it goes off at 30 degrees. So I'm going to call this theta of the ball relative to the earth. So I can still do relative velocity addition if I'm trying to learn about the ball relative to the earth. Oh, wait, what are we trying to learn about? We're trying to learn which way to aim. So we're trying to learn about this angle, which I'll call theta ball relative to the train. I want to learn about that. You can see even me, I'm like really confused right now. So let's go through this problem. I'm going to write down my relative velocity equation. Notice it's not relative speed equation. We have to do velocities. So I'm going to say, look, I'm trying to learn about this one. So I'm going to say VBT. Maybe I'll do all lowercase here. I'm kind of mixing up my cases. I apologize. Let's make them all consistent here. Again, uppercase, lowercase doesn't matter. I apologize. But let's try to at least be consistent. Sorry about that. Okay, in this case, now we're all in the same case. Look, BT, do not overthink it. Do the same process you always do. B is going to come first, so that means I'm going to need a VBE. T is going to come last, so I'll need a VET. Make sure I didn't screw that up. So the idea here is I'm trying to learn about this thing because I want to know its angle. I can see that the E gets squeezed out. Notice I might need to immediately flip this. So I see that VTE is negative VET. Whoa, I think, I want oh my gosh, I'm getting tired. I see that VET is the opposite of VTE, which would be negative 20. So I know everything about this one, both I hat and J hat. Right? It's 0 in the J hat, positive 20 in the I hat. So I know everything about this one. So this vector is done. Here's where it gets tricky. Why don't we write these in another way? I know that This is, oh my goodness, this would be VBT, the speed, times cosine theta BT in the I hat plus sine theta BT in the J hat. That's what this vector is. I know this part of it, but I don't know the angle. Let's go to the next vector here. VBE, I know the angle, but I don't know the speed. So that one I would write VBE, which is an unknown, times cosine 30 in the I hat plus sine 30 in the J hat, and should have the degrees on there. Notice in this case, whoops, maybe I'll put this one here so you can see it. That's 40 meters per second. Right now, I don't know this angle and I don't know that speed. Let's keep going. Plus, I do know ET. ET is the opposite of TE, which gives me negative. I'm getting a little bit lazy with the sig figs just so I can fit this in here. At first glance, it looks like we have one equation, one unknown. However, we can actually set the I hat parts equal to the I hat parts and the J hat parts equal to the J hat parts to get two equations. So if I do that, I'm going to just write the I hat part here. So I get 40 meters per second cosine theta BT. This is the I hat part, ignore the J hat. The next term would be VBE cosine 30 degrees I hat. And then ignore the J hat. We're just doing the, I can ignore the I hats because they're all going to drop out. Sorry. We're only keeping the I hat terms. Each term will have an I hat. Therefore, I don't need to write the I hat because it cancels out. I'm going to say that again. We're keeping only the I hat terms from this equation. Because every term will have an I hat, I can cancel it out. Independence of XY motion. Finally, we get a minus 20 meters per second. There's one equation, two unknowns. The other equation comes from the J hats. We're going to keep only the J hat terms because every J hat term has a J hat. The J hats drop out and I get see, this is the J hat term of this one. Here I get now you can see you really do have two equations and two unknowns. Now in this case, what might you do here? Let's see. For me, I guess one of the things I might do is if you're looking for this, you might say take a ratio. But in this case, the VBE won't cancel out because this term doesn't have VBE in it. You could solve this term for VBE and plug it into that term. And when you do that, you'll get a term here that has a cosine theta, a term here that has a sine theta. And at that point, you might be saying, well, geez, how can I solve this? One method would be to write a computer program and solve that equation. Another trick is to square both sides. You wouldn't think to do that. Obviously, the solution is all written up, and I'll put a link to the solution. That way you can find it. But in this case, right, you could actually square both sides, and one side will have, actually, this is probably what I would do. I'd square this entire equation, and I'd square this entire equation. And this, to me, seems like the easiest way to do this. Well, more on that in a second. But when you do that, you're going to get a cosine squared and a sine squared. When you add these two equations together, the sine squared plus cosine squared equals 1. Now, at that point, we'd have a bunch of junk over here, but we could do a quadratic formula on VBE. Once I get VBE, I could plug that back into here and get this. See what I mean about this being a hard problem? Relative velocity seems really easy at first until you get to realistic, real-life problems. This is a good problem. Which way should you aim so the rocket goes where you want? That's a good problem. It's hard though. So I hope you can see this. I'm gonna go ahead and set this up on the next board. So I'm gonna take these two equations over there and do that. If you can follow along without me, just go ahead, do whatever the heck you want. Come on. Okay, so I'm just taking this equation over here. I'm gonna be lazy and drop the units and put them back on at the end. And I'm gonna be lazy. Well, I'm not gonna be lazy with this. Okay. So in this case, what I said was square it. So I'm gonna square it. Oh, what the heck? Let's leave the units in. I'm gonna square every term. Okay. Now I'm gonna take the other equation and rewrite that over there. Whoops. I think it ended up being minus 20. Sloppy. All right. So here's where people get into trouble. Usually, if I square everything in this equation, I got to square this, square this. The problem here, you can't just square each of those terms, right? You got to square each side. So you got to square the whole thing. So you get this squared, and a cross term. And that's what people forget. But first, I'm going to just show you what I meant by squaring them and adding them together. On this side, notice you're going to get 40. Oops, that's blue. 40 meters per second quantity squared times sine squared by the way, I'll tell you a shortcut after the end. You might be saying, oh, could I have just used the law of cosines? Yeah, I guess I told you the shortcut now, but if you don't know the law of cosines, this works too. All right. Maybe you can even do it with law of sines too. I haven't thought through. But here I'm just going to say this is VBE cos 30 minus 20 meters per second. Oops. Squared plus that thing. And what I was saying is this term goes to 1. And that's how you can get rid of one of the unknowns. Now you might be saying, why don't I want to solve for this. Why don't I get rid of the other unknown? You could do that. This just came to my mind. And so it seemed nice. And it actually seems less messy to solve for VBE in my brain. So I'm going to do that. Obviously, there's probably a faster way, but in this case, let's just keep plugging along. I think the solution, I did it the other way, but whatever. So now you'll have two different versions to look at. And in this case, oh, I should have put a degree there. Okay. So in this case, when we square this term out, I should get VBE squared cosine squared 30 degrees. You might be saying, don't you just plug in that? You could, but I think you'll see something interesting here when I do it this way. I'm going to get a plus. Now remember, it's a minus in here, but when you square it, it's negative 20 times negative 20, which is positive 20 squared. And then notice we get this cross term in here. Plus 2 VBE cosine 30 degrees times negative 20. And then we still have this last term here. You don't have to do it this way, but you could have started plugging in numbers. But I wanted to show you, I mentioned you could use the law of cosines. I want to show you that we basically just derived the law of cosines. Look here, I've got this VBE squared sine 30. Whoops, that's not a degree symbol there. That should be a squared, right? But look, I get a sine squared plus cosine squared here. times VBE squared. So you end up getting equals, I get that comes from this term and this term. Take a second to believe that. VBE squared, cosine squared plus sine squared, that's a 1, right? Do you see that? I hope so. That's where this term came from. Now I got the second term. And then I have, notice I get this weird cross term here, and notice I got a negative there. So, but that's something like this, minus 2. How would I just leave it as this? Plus 2 VBE negative 20 meters per second times cosine 30, which this makes it look a lot like the law of cosines if you look it up. And if it helps, you can kind of draw a picture of this thing to try and help visualize it. So in this case, I'm going to throw it this way. This is the velocity of the ball relative to the train. I'm going to add to that the velocity of the train relative to the earth. And notice what gets squeezed out when I add these two vectors. The t gets squeezed out, and the sum of those is this way. The velocity of the ball relative to the earth at a 30-degree angle. I want this 30-degree angle. What angle do I need to use right here? And it looks like it's about 45 degrees or something. I hope this kind of helps make visual sense out of this problem. Now, in the end, I think what I got for VBE was, if you finish this problem out and solve it with the quadratic formula, everything in here is numbers except for this. Notice you get a VBE squared and a VBE. Use the quadratic formula and show you get, I think it's 56.05 meters per second. And from there, I believe, let me just look this up so you've got it all in one spot. The ball relative to the train, which is, this is which way you aim. What did I get for that? Let me just check really quick. 44.5. 44.5 degrees. So about 45 degrees. So the ball is going to come off here faster than 40, right? You throw it this way, which is about 40 meters per second. You add the 20 meters per second to it, it's going to come flying out here at about 60 meters per second. And if you angle it, if you aim at 45 or 44.5, it will come off the train at a 30-degree angle relative to the earth. So that's the problem. I'm going to show you the sim real quick. I'll put the links up, and then, yeah, that's as hard as they get. But that's pretty hard. So let's do this one. So relative to the earth, this is what it looks like. Notice that I'm going to pause. Well, I'm trying to show you here. This angle right here is the 30 degrees relative to the earth. So if I, right now it's moving, this is the velocity of the, oops, that's the velocity of the ball relative to the earth is 56. Let's clear that out and let's rerun it from A's perspective. So the train, right, if we look at this from the train's perspective, the earth is moving backwards at 20. And notice in this case, the angle is a little steeper. So this angle is that 44.5 degrees. So you aim at 44.5, and in the end, it's going to come off at that other angle of 30. So if you aim it that way, it's going to come off this direction. I hope that makes some sense out of this and all that garbage there.